Okay, so hi everyone. I'm back and we will be talking about the scalar product form of a plane. So the scalar product form is actually in a sense the trickiest form for a plane, but I will try my best to convey the idea. Okay, so first of all, let's talk about the computation of the scalar product form, the numerical picture. So the numerical picture, right, is r dot n equals to d. So we need to provide four numbers. So the four numbers is going to be the three components of the n vector as well as the d. So so what is this? So how do you compute the three n? So let's say we want to convert our vector form into our scalar product form. How do we do so? We can do so by by taking n equals to b cross c. And why is that so? So n is the normal vector to the plane. So if I draw the plane over here, then n is a normal vector. And normal vector by definition is the vector that is perpendicular to the plane. So yeah, so why is it a cross product? It's because if we can revisit the definition of a cross product, right? So the definition of a cross product in the previous lessons we talked about it was that if you have your vectors a cross b, right, then the geometrical picture of a cross product is that is equal to the magnitude of A, the magnitude of B, sine the angle between A and B, times the normal unit vector. So this normal unit, you see that it precise, and the sign convention of normal unit vector is determined by the right-hand rule. So you can see that that's the reason why the normal vector can be taken as the cross product between B and C, because B and C are vectors that are parallel to the plane. So B and C are vectors that are parallel to the plane. So if we take the cross product, right, between these two vectors, we're going to get the normal vector. And the normal vector, the direction of the normal vector is precisely defined as the normal to the plane that is spanned by B and C. So if it still doesn't help, then let's bring up this visualization over here. So we have the plane over here, right? And with the B and C vector shown by AB and AC. Then if we take the cross product between B and C, then you can see that if I look at the plane from any angle, okay, so let me just remove the A vector. So take a look at so right now this long vector is the cross product between B and C. So if I take a look at the plane from any angle, you can see that this long vector, this normal vector is perpendicular to the plane. If I move around, you can see from it applies for any angle, right? So any angle I choose to look at the plane from, right, from the side, then the vector is perpendicular to it. And if I move B and C around, then you can see that the cross product changes accordingly, such that the long normal vector is always perpendicular to the plane. So yeah, that's the visualization for the cross product. So the cross product, right, numerically, we covered how to calculate it in the cross product video. It's just it's defined as so this bx, by, bz, then cx, cy, cz equals to by, cz minus bz, cy. Then the next one will be bz, cx minus bxc z. And the last one, the last component, right, will be bxcy minus bycx. Yeah, so this is the cross product. So that's how you numerically calculate it. Okay, so for the geometrical picture, this is the part that's tricky. So for the geometrical picture, I'll appeal to you to first think of it in two dimensions. So let's say we restrict ourselves to the z equals to 0 plane, right? So now we are thinking in 2D, in the 2D world. So we temporarily restrict ourselves to the 2D world. Then what would a line look like, right? So if we have the Cartesian plane, So we've got x and y coordinates. Then a line that not necessarily passes through the origin will be something like y equals to a, or something like y equals to mx plus c, right? So this is the linear equation, but if we think of it from a different perspective, right? So y equals mx plus c. Let's try to write it in a different form. So let's say we have the normal vector to the line. So let's say we have a vector that is perpendicular to the line, and let's call it the n vector. Okay, and let's say the n is a unit vector, meaning that the head over here indicates that the length of n is equal to 1. Then the position vector of any point on the line goes to x, y, 0, right? 0 for the z component because we are restricted to the z equals to 0 plane, the xy plane. So if we compute r dot n hat equals to some fixed number, let's say d, then expanding this out in terms of the components, right? And the last component is 0 if we remember that we are restricting ourselves to the xy plane, then this equals to d, and rearranging it simply gives us nx plus y and y equals to d. And this is precisely the form of y equals to mx plus c, because this is just minus nx over ny x plus d over ny. So this is the form, this is of the form mx plus c, right? Where c is this term and m is this, the gradient is this term. So what have we figured out from here? We have figured out that one way to describe a line in 2D space, right? In 2D space is to write y equals to mx plus c, right? We're all familiar with that. But another way, right, is to actually to write in terms of the vector that is normal to the line, right? So it's perpendicular to the line. And let's say we have such a vector n hat. Then if we write r dot n equals to d, then we get it's another way to describe the line. So this, why do I write it like that? Why do I go through the hassle of writing it like that in 2 dimensions, right? It's because this easily carries over to the 3rd dimension, where instead of having a line, we have a plane. So yeah. So another thing that I want to mention over here is that because n is a unit vector, d is actually the shortest distance from the origin to the line L. And the reason, so the shortest distance in this case will look something like this, right? And the reason why that is so is because of the definition of the dot product. So if we have the line and we have this r, then recall that if we have the unit vector n hat, then recall that geometrically r dot n equals to the length of r times the length of n times the cosine between the angle. And in this case, the n hat, right? The length of n hat is 1. So this is just r cosine theta. So r cosine theta is precisely this distance to the line, because r is a point on the line, right? R is a point on the line. Then the length of r is the length of this arrow. So r cosine theta is the length of this. So this is r cosine theta. Yeah. So and this is equal to d. So d is the interpretation of d is that this is equal to d, right? And the interpretation of d is that it's the distance from the origin to the line, the shortest distance. Yeah, but this only applies if n was a unit vector, right? If n wasn't a unit vector, then this step wouldn't be valid because this step depends on the fact that n hat equals to 1. So yeah, so I went through this trouble of talking about it in 2D because it's easier to draw, right? And it's easier to write is and this equation that we write is immediately recognizable as the equation of a line because we're all familiar with that. But now you can carry it out over the 3D, right? Actually, it's more or less the same idea. So 3D. So now we're no longer restricted to the x z equals to 0 plane, right? No longer restricted to the xy plane. And now r dot n is going to describe a plane. So if let's say we have a plane with a unit vector n hat. So let's say we have a plane with a unit vector n hat. Unit normal vector n hat, right? Then we have the origin. Then for any point on the plane, r dot n hat is going to be the shortest distance from from the from the from the origin to the plane. So if let's say let's say r was like a point like this, then the shortest distance is going to be this distance. And yeah, but now because we have brought ourselves to the third dimension, right? Because we have brought ourselves to the third dimension, then we have x, y, z dot nx, ny, nz equals to d, right? So we're no longer restricted to z equals to 0 plane. Then the equation that we see is actually this equation. And now this is no longer automatically recognizable as equation. I mean, this is precisely you might not recognize this equation, but this is precisely the Cartesian equation, Cartesian form of a plane, right? So we've brought ourselves nicely. We've just converted the scalar product form to the Cartesian form. And how do we know this defines a plane? To understand why this defines a plane, we look at the degrees of freedom and constraints argument again. So we start out with 3 degrees of freedom, x, y, and z, and then we subtract away one equal sign, right? One constraint, which is this equation, and hence we are left with 2 degrees of freedom, and this 2 degrees of freedom defines a plane. So yeah, so the upshot of this is that, can you see that this scalar product form is actually just a way of writing out the Cartesian form in a compact manner. So yeah, so that's the key takeaway. Yeah, so if we can do a quick recap of the 3 different forms again, right? We started off with the vector form where we learned the interpretation of a little explorer that wants to explore the plane. How do we let him explore the plane? We first bring him to any point on the plane, and then we give him directions to travel along the plane. In this case, the directions are the vectors b and c. So these directions are parallel to the plane, and we let him explore in these both directions, traveling along any distance he wants, right? By giving him the parameters lambda and mu. So we say, hey, here's your vector b, you can travel in this direction, right? Or you can travel in this direction, or any linear combination of them, right? So you can travel any amount in b followed by any amount in c. And if b and c are not parallel, then that would span the entire plane that he can explore. So that was the vector form. That's a very nice geometrical picture. Then after that, we learn how to convert the vector form to the scalar product form. And how do you convert it? We need to compute a normal vector by taking b cross c. And why is a normal vector defined this way? If you look at the definition of a cross product, right, you will revisit the video, then because b and c are parallel to the plane, n equals to b cross c will be the normal to the plane, right? So that's owing to the geometrical picture of the cross product. So if you're unsure of this, then please revisit the cross product video. Then after that, we take our r and we dot n, right? And it equals to a constant. And how we can find this constant? We can take any point on the line. In fact, right, you can check that because because this n equals to b cross c, right, you can check that this means that b dot n equals to 0 and c dot n equals to 0. So after that, we are left, if we substitute this vector form into this equation, then we can see that actually, right, we get a dot n equals to d. So actually d is, another way to write d is a dot n. Yeah, so so this d is a constant, right? So we, by providing these four numbers and writing the scalar product form r dot n equals to d, we actually define a plane. Now that was not immediately obvious, so we stepped back into the two dimensions, right? And we drew an analogous way of defining a line using the dot product, right? And we saw that it matched our familiar intuition, our familiar idea of what a line is, which is y equals mx plus c. Then from there, we use the same equation, but moved into the third dimension. And then if we write out r equals xyz in a column format, as well as the n vector, the normal vector, then we obtain this equation, which was precisely the Cartesian form of the plane. And so then that led us to think, what is the Cartesian form of the plane? Why is this equation? Why does this equation describe a plane? And if you had understood the Cartesian form of a line, then the degrees of freedom and the constraints argument, then you realize that, hey, this is actually it's precisely the same argument, just that instead of having two equal sign, I have one equal sign. So in the end, I'm left with 2 degrees of freedom for x and y, right? Which is the plane. So maybe if you could listen for a little bit more, right? So if we take a look at this equation, let's say I let you choose any 3 values of x, y, and z that you want that must satisfy this equation. So maybe you take a look at it and you say, hey, x seems pretty free. Let me choose the value of x, right? So now x is fixed. So let's say x equal to 1. Then you move on to the next variable. Is y free for me to choose? And in fact, y is free for me to choose because y is still free for me to choose because it's not constrained fully yet. But then now you move on to z, right? And then you look at z and you think, wait, can I really choose any value of z that I want? No, because I have already chosen the value of x I want. I've already chosen the value of y that I want. And since x, y, and z must satisfy this constraint equation, then z would be fixed by it, right? Z will be fixed already. So I cannot choose the value of z I want. So you see that we had 2 degrees of freedom for x and y. Or if we wanted, we can choose y and z first, and then we'll be fixed for x. But either way, right, we can only choose 2 free coordinates. And that corresponds to the 2 degrees of freedom over here. And yeah, so that's the overview of our three equation formats for a plane. And in the next video, we'll be talking about several other things we can do with planes, and we'll be finding the intersection between planes and between lines as well. So if not, yeah, see you in the next video.